The canonical pendulum is when we have a mass at the end of a string and we're spinning it around. You've done this before. This is the tether ball. This is swinging your little girl around by your ankles. This is the same as when we had gravity and tension interacting when we were accelerating in a car and we were looking at the fuzzy dice hanging from the rear view mirror as we accelerated in the car. It's the same thing. What is it? Is it hard? Well, we recognize it's a dynamics problem. Oh shit, man, I know I'm going to have to say the vector sum of the forces is equal to mass times acceleration. Well, what are the forces? I have a mass. I have some tension in a string. And I have some gravity pulling on it. Those are the only two forces. And then I have acceleration. I can say, look, the acceleration must be in this direction. In two examples, in our past example, we were accelerating in our car in this direction. We just said the tension plus the force of gravity are the vector sum of the forces. Oh, so they better be in the same direction as the acceleration. So this is tension, force of gravity, and this is just the vector sum of the forces. And we know that's equal to mass times acceleration. Before it was linear acceleration, we were accelerating that way. Now we're still accelerating it this way, but the object is moving in a circle. And so the only difference is we just say this is equal to v squared over r. This itself is not a force. The forces come from the tension and gravity. It's a big mistake for students. They identify mv squared over r and they say that's a force. No! That acceleration is because of the forces. And so in the protocol, there's this one step where you say, are we in equilibrium? And here we're moving at constant speed, but no, you say we're not in equilibrium because we're accelerating into the center of the circle. And then there's a very important one. What is the direction of the acceleration into the center of the circle? And so this is really, really basic to solving the problem, because think about what it would be like if instead of swinging my little girl in a circle, we had lost our frisbee up on this rooftop and I was trying to accelerate her in that direction. How would that be different as I'm swinging her around by her legs to accelerate her in that direction? Well, then the tension before plus the force of gravity, oh, that's not going to work, because I know the vector sum of the forces must equal mass times acceleration, right? It's got to be in this direction. So what does that mean? That means the tension has to be super big in order for the tension plus the force of gravity to be accelerating her that way. That would hurt her ankles. So I don't know if I should do that. I'll have to find a different way to get the frisbee off the roof. Why did I do this? Because all of these dynamic problems boil down to the same thing. The vector sum of the forces, and a force is an interaction between two bodies, is equal to mass times acceleration. What are the directions of the forces? What is the direction of the acceleration? So in these problems, how do you find the velocity? How do you find the acceleration? How do you find the tension? We don't tell you any of those. All you know is you can see something spinning around like this. We know two things. We know the force of gravity, so that gives us scale, and we know that the angles of the tension is the same as the angle in the string. And so if I were to do this problem, I would say here's the tension, here's the force of gravity, which is equal to mg. I know that. And then I know this angle must be equal to that angle. So I can find out what this is. This is the vector sum of the forces, and I can say, oh yeah, it's
From the triangle, we can see that in this scenario, the vector sum of the forces is about the same magnitude as the force of gravity, mg. But you could see that depending on the angle of the tension, the vector sum of the forces could be much greater or much less than the force of gravity.
Then I can just take that number, the vector sum of the forces, and set it equal to ma. And for that rotating canonical pendulum, that tether ball, that's going to be mv squared divided by r, or m omega squared r. And this is, of course, the same for a car on a frictionless track that's trying to go around like a freeway off-ramp where here you're looking at the back of the car as it drives away from you around this track. Because now this is in tension, this is the normal force, and you know what the normal force does? It adds with gravity so that you don't accelerate up or down, but you got to accelerate in this direction. Oh, and you get the vector sum of the forces, which is equal to mass times that acceleration. What kind of acceleration is that? It's centripetal acceleration.
So we take a look at the F-22 Raptor. You see the back, you see the little feeties on the back here, how they can control the air, and Newton's equal and opposite law, that the force they put on the air puts the opposite force on them. Okay, so we take a look at this turn, and we wonder how many G's the pilot is feeling right there, and what the forces acting on him or her are. And we get a good view right about now. If it's traveling in uniform circular motion right now, the acceleration is in this direction, and that acceleration comes about as a result of the two forces acting on the plane. And that would be the normal force, or the force of lift from the wings, and the force of gravity. So can you estimate the acceleration of this pilot right now? And if the pilot is a man of 70 kilograms, such as myself, what would the normal force be acting on his body? We need to add these two forces, nose to tail, so that the sum of the forces, the net force, is in the same direction as the acceleration. When we do this, we can see that the normal force acting on the pilot's body is much greater than the force of gravity. And so flying one of these planes is a physically very demanding process. We can also see that the centripetal acceleration inward is much greater than the acceleration of gravity. And we can estimate these ratios from this triangle and see that it might be 5 gravities, or 50 meters per second squared.